Hello everyone, my name is Ali Eric Chinonso. I'm from Huazhong University of Science and Technology, Wuhan, China. My department is cybersecurity. So today the topic of our presentation is RS-FEDRAD, Robust and Scalable Federated Ransomware Detection using TTP-Enhanced Dataset. So we are going to go through this agenda. We look at the introduction to ransomware and problem, and we look at the traditional detection approaches. Then we move to the research gap, and then we also discuss our proposed framework before we move to result and discussion. Then finally we take questions and answer. So ransomware attacks have evolved over the years into a major cybersecurity threat affecting individuals, organizations, and critical infrastructure. Traditional ransomware techniques such as static analysis or hybrid approaches have been employed, but they have shown limitations. So this research proposes a method that integrates federated learning, deep learning technology in combination with feature-enriched datasets. This is meant to advance ransomware detection and give room for next generation robust and scalable detection practices. So let's have a look at the brief evolution of ransomware. So the first modern ransomware can be recorded in 1947 when we experienced attack in form of worms and viruses. From then, ransomware have evolved and improved into what we know today as modern day ransomware. Now, this modern day ransomware started around 2010 up to now, and they have developed into sophisticated capacities and capability which they employ to evade detection and to continue to cause havoc into individuals and infrastructures. So these qualities include polymorphism, encryption, and finally obfuscation. So the modern ransomware actors apply this capacity in order to continue to evade detection. Okay, so we look at the traditional ransomware detection approaches, just as we have introduced the static analysis, dynamic, and hybrid. Now we have said also that the static analysis is like a signature-based approach that compare the database with known signatures. So the dynamic analysis method is more advanced as it examines the signatures during execution. So also the hybrid approaches most times involve combining the static and dynamic, but also it involves combining two deep learning or neural network models. That's like we in this approach we are using CNN and LSTM. So we have analyzed the current research gap which goes with centralized architecture, because most approach uses centralized architecture, they introduce privacy and scalability issues. Also, just like we said, static or signature based are inefficient in detecting modern day ransomware. So also why the dynamic and hybrid are more advanced and even detect 0-day cases, but they are limited by lack of comprehensive feature set. So when we look at company C in this diagram, company A and company B, so we see they all have one access control. They are all going through access control to locate central data repository. So this can bring scalability and privacy issue, especially as in regard to regulatory policies. So now there's a question, is federated learning a solution? Yes, federated learning is a big part of the solution because it offers several advantages. Now what is the advantages? We can see first, it allows multiple clients and organizations to train collaboratively without sharing their raw data. So with federated learning, organizations and firms or companies can come together and develop a more advanced collaborative model where everyone can benefit without sharing their privacies. So it also makes them to adhere to regulatory compliances, and improve detection. Also, with federated learning, it will be easy to scale the model and makes it robust. So in this slide, we introduce our proposed framework, the RS-FEDRAD method. So this framework consists of 4 modules or 4 stages. So in the dynamic analysis module, we dynamically analyze known ransomware attributes like to extract API calls, DLL, and mutual exclusions. So these are the major attributes that ransomware apply, the modern ransomware apply. Now, which is what we call the feature set module. So after mapping this, extracting this feature set, we further enhance them because our target is to get a feature enriched data set. We further enhance them by mapping them using the MITRE attack framework, where we map them according to their tactics, their techniques, and their procedures. And MITRE attack framework is a well-recognized cybersecurity arsenal for extracting, sharing, and applied threat intelligence. So we map this dynamically analyzed ransomware attributes to their tactics, technique, and procedure using the MITRE attack framework in order to further enrich the feature space. After mapping, we move to the detection module, where we feed this into our detection model, combining LSTM and CNN. So from this, our detection module feature engineering takes place, and we are able to classify if they are ransomware or they are benign. So in this slide, we introduce the federated trailing architecture, of course, which will ensure that our model is in a decentralized and privacy ensured mode. So here we propose the client. So each client will train in their local data set and then send the update to the aggregator. Now this aggregator collects the update from each client and combine them, then transfer it to the global model. So our global model here is represented by the Flower server. So this Flower server collects this update from the aggregator and combine all of them, then share it back to each client. So each client is able to receive a copy of the combined synergy between all the clients, and they learn from each. At the end of the day, we are having an improved model that is shared to everyone without compromising privacy. So here is our hyperparameter tuning, the selection that we have made for hyperparameter in order to get an optimized and improved detection. So we move to the evaluation result. We checked our model using known metrics, state-of-the-art metrics, including accuracy, precision, recall, and F1 score, among others. So after training for 10 rounds, we recorded an impressive 99.9% accuracy at the 10th round, and also the federated average accuracy of 99.52 across the round. So this is a visualization of accuracy, precision, recall, performance. Here we compare first figure label A. We are comparing centralized architecture against federated architecture. So we can see that our model performed very excellent because we applied a comprehensive and feature-enriched data set. We can see that both the centralized and federated architecture performed well. However, the federated learning did better, of course, and it's expected because it learned from a global model. You can see the distance between the accuracy of the centralized model and that of the federated model. In terms of ransomware detection, very minor difference is very, very effective, because if one ransomware affects you, it's as good as 10 ransomware affecting you. So we are able to kind of show the improvement in combining models together. Then here we also know the the security of infrastructure in terms of digital space is very important. So we look at the digital perturbation that could come. So we compare our model in adversarial training. We have employed FGM and BEAM architecture, which is a black box and white box attack method to check for adversarial perturbation. So our model was able to maintain a stable performance even in adversarial condition, as recorded with stable accuracy precision along all metrics. So here we look at the federated averaging style. We selected the federated averaging style while we considered other averaging strategy like Fed pros, Fed average mean, and Fed median. Also here, to ensure the scalability of our system, we increase the number of clients from 10 to 15 to 20. So we can see that our model maintained a stable performance along the increasing number of clients. Or we compare our method with state-of-the-art dynamic deep learning approaches. Our model maintain optimal performance, especially in terms of accuracy and precision, while maintaining the same level in terms of recall and F1 score. Similar experience is shared with deep learning approaches, and here is our table of comparison with deep learning and federated approaches, showing our system optimal performance against state-of-the-art approaches. So here is where we conclude. We now take your questions and answer. Thank you.